Welcome back to ME 760, Engineering Analysis 1. So today we will conclude with the chapter 4, the double and triple integrals. As I stated last time, today we will just show how to convert from or transform from a triple integral, which is volume integral, to a surface integral. And this is what we call divergence, or sometimes we name it as Gauss theorem. So the divergence or Gauss theorem states that if you have a volume, and this is volume V, this volume is bounded by a surface S. If we use a unit area here, this will be the normal to the surface. Imagine this is like a balloon, and you blow air inside the balloon, so the volume will be the volume of air, and the surface will be the surface of balloon. You with, let's say, a marker, black marker, you put an area delta A on the surface of the balloon, and then the unit normal to the surface will be N. So the theory says that if you have divergence of certain function f evaluated inside the volume, so divergence of f evaluated over the volume can be correlated or equal to the same function f dot n dA, where n is the normal and dA is the differential area. So nDA is dA vector, so the area vector dot A vector. So n is just the unit normal to the surface in the outward direction. So to give you an example for application for the Gauss theory, we will look at the heat equation. How many of you here are mechanical engineers? So there is quite a few. So you knew Fourier law for heat conduction. Fourier law for heat conduction. It is the heat flux vector here is equal to negative k gradient of T, where T is a function of, let's say, x, y, and z, and maybe the time t. So temperature is a scalar quantity, and the gradient here is a vector quantity. So this is the heat flux vector. And you knew that if you have a temperature gradient, let's assume that this is x, and in one dimension t of x, if you have a temperature gradient like this, and you have a unit or a surface area like this, unit surface area, the heat flux will be going from the higher temperature to the lower temperature, and the gradient is in the opposite direction. So this is why we said that Q is proportional to the gradient, but it's in the opposite direction. This is why we have negative sign. And the proportionality constant here is K, which is the thermal conductivity for the material. So let's write the heat equation. We knew that if you have certain volume, the rate of gain of energy inside this volume, of energy in the volume V. So if you have this volume, the rate of gain of energy in volume V should equal to negative the net rate of heat loss. So you have the losses term. Losses term is the heat losses, and you put negative here because this will decrease the energy inside the volume. And what increased the energy inside the volume is just plus the rate of heat generation. from any sources in volume V. So if you have any heat source here like a heater, and then you have a refrigeration inside to cool down, so the net rate of heat losses will be heat losses to the environment, for example, and the sources of heat inside here is equal to the time rate of change. How we write it in this format? So the time rate of energy gain inside the volume, so we have to integrate over the volume, and this is Cp, which is what? Specific heat at constant pressure, multiplied by what? Multiplied by temperature of X, Y, Z, and T, multiplied by what else? Multiplied by the density. Yes, because it is mCp delta T. So M is here what? M over V. So this is per unit volume, and you have to integrate over what? Over volume to give us this one. And what's the losses now? So if you have a surface like this, the losses will be what? The heat flux integrated over the surface area. Yes, because the heat flux is heat per unit time per unit area. When you integrate it over area, it will give you heat per unit what? Time. And this will give you heat per unit what? Time. So this is what? Q dot N dA. And the sources is what? This is over surface, this is over surface, is Q dV. So any source, volumetric source, so heat per unit volume, for example, per second. You have a heater, gives you heating per unit volume per unit time. So now we can transform this according to the divergence equation, and d by dt for the volume integral of what? Cp T rho delta V is equal to negative, and we'll transform this from the equation over there, so it will be the divergence of what? Divergence of Q dV plus the Q dV. Okay, guys? And what's Q? So this is divergence of what? K grad T dV plus Q dV. Then if you move this one, so this is, if you move this one to this term, and let's assume that Cb is constant, density is constant, the only function of temperature is T, we can get this d by dt inside, and we will have the volume integral of dt by dt plus what? Minus, because plus plus is minus, when you move it to the other side it will be minus. Minus what? Divergence of K grad what? Grad T minus Q, all evaluated over the volume equal to 0. So you have some function evaluated over an arbitrary volume. Arbitrary volume means I can take the volume to be the volume of this, let's say, room, or I can take it as a volume of cell, or a volume of a reactor, or whatever volume. So any function evaluated over arbitrary volume equal to 0 mean that this function is equal to what? Is equal to 0. So now the function is equal to 0, and this yields the heat equation, heat diffusion equation, and the heat diffusion equation is just d by dt of x, y, and z and t is equal to 1 over Cp rho divergence K grad T plus Q over Cp multiplied by rho. This is the well-known heat diffusion equation. Heat diffusion equation. Okay, guys? So what if you have, for example, no source, and you have also K is constant. The thermal conductivity with respect to position is constant. Let's say uniform material that you are using with uniform K. So this will yield what? dt by what? By dt equal to 1 over Cp multiplied by rho. And K is constant, so it will come where? Outside. So we can put it here. And this will be nabla square what? T plus Q is what? Is 0. So this is the heat diffusion equation when you have a constant K and 0 source. Okay, guys? Another application, if you have a function, the Laplacian of a function equal to 0, and this function might be a potential, for example, a potential function or a harmonic function. So this is, it's called the Laplace equation. And nabla square is called the Laplacian. So this is the Laplace equation, and nabla square equal to Laplacian. So if you have nabla square f equal to 0, this is Laplacian, Laplace equation. And if it equal to a function of x or function here, this is called Poisson equation. Okay, guys? Like what? Like in electrostatic, nabla square what? Phi equal to negative rho over epsilon naught. So this is in electrostatic, for example. So if you have a function f equal to gradient of some function f, for example, so the volume integral of nabla square f dv, because if you substitute here with divergence of f, and f is equal to gradient of f, so this will give you divergence of gradient of f. This is nabla square f dv, and this will be equal to what? The surface integral of what? Gradient of f n dA, and this is equal to what? When you, what's this from last chapter? If you dot product a unit normal with a gradient, this will give you what? The differentiation of the function f with respect to what? With respect to n. This is we know from last chapter. So this will give you what? On the surface df by the what? By dn evaluated over the surface, and this is equal to 0 if you pick up a potential function, or let's say a harmonic function like this. This is one of the applications. So how to prove the Gauss theory? So the proof, so we'll give another proof different from the one in the book. So you can use either this one or look at the book and use the one in the book. So divergence of f integrated over a volume dv is equal to the surface integration of f dot n hat dA. So let's assume that we have n, the unit normal is just, if you have a unit, this is x, y, and z, x, y, and z, and let's assume that you have your area here like this, and this is again z, so this is the unit normal, and the unit normal makes alpha, so this is x, y, and z, it makes angle alpha beta, and gamma with these three coordinates. So what's the component of n, vector n, with the x-axis, with the I? So we knew that n dot r, n dot I is equal to cosine what? Cosine alpha. And n dotted with what? J is cosine what? Beta. And n dotted with k is cosine what? Gamma. Somebody will say why? Because n dot I, n, what's the amplitude of n? 1. And what's the amplitude of I? 1. So it will be the amplitude of this, the amplitude of this, multiplied by cosine of the angle between those two vectors. Cosine of the angle between n and x is alpha, beta, and gamma. So this is why you get this one here. So this will be what? This will be cosine alpha in the I direction plus cosine beta in the jth direction plus cosine gamma in the kth direction. So now, and let's assume that the function f is just f1 in the I direction plus f2 in the jth direction plus f3 in the kth direction. So now apply this one. So divergence of f will be what? df1 by what? By dx. Okay, guys? And if you dot it with this one, will give you what? No. So, and this is df2 by dy. This is df3 by dz. This is just the what? Divergence of f. Yes, guys? And volume is what? dxy, dx, dy, dz. And the surface integral will be f. So it will be f1 what? Cosine alpha plus f2 cosine what? Beta plus f3 cosine what? Gamma, all multiplied by the area, and the area is what? dx, dA, dx, dy. Or ds, not dx, dy, sorry, ds. Because I am evaluating over an area ds. ds or dA over there. So let's put it dA. So this is the area dA in space. Okay, guys? Do you have any questions so far? Guys, do you have any questions so far before I move on? Okay, so now, if we can prove that the first part of the integration, df1 by dx, dxy, dz, is equal to the first part over there is what? f1 cosine what? Alpha dA, and we will call this 2a. And if we can prove that df2 by dy, dx, dy, dz is equal to the surface integration for f2 cosine what? Beta dA, and then df3 by the what? By the z, dx, dy, dz for f3 cosine gamma dA. So if you add those three, it will give you those three, which is the right hand side equal to the left hand side. So we have to prove this. Okay, guys? So for this sake, we will look at this one first to see. We will see how we will do it. So in order to do it, we will look for a surface to integrate over. And this surface is just, here it is. So we have a surface like this. So the lower part of the surface can be represented by a function g of x, y, for example. And the upper surface here is h and x and y, and this is something like equator here. So if you get the projection of this surface on the lower plane here, which is xy, it will give you a region R. And now we will have our surface here, delta A or delta S, and this is the unit, this is the K direction, and this is the unit normal N, and there is an angle here, gamma, between the angle gamma between N and Z. So for the lower part here, this will be again the unit, the area dA. This is the K direction, and the unit normal is like this, downstairs here. So N dot K is equal to what? Cosine what? Cosine gamma. For what? For the upper one. And N dot K for the lower one will be what? Minus cosine gamma, because gamma is what? Is greater than what? Huh? Is greater than the a 90 degree, or because this is the angle here, this is the angle here. Okay, guys? Okay, guys? So now, and the projection of this area on the surface on the region R, the projection is just what? dy in this direction and dx in this direction. So now let's try to see how we will represent this. First of all, we will assume non-re-entrant surface. What we mean by non-re-entrant surface? Non-re-entrant surface is a surface like this. Re-entrant surface is a surface like this. What does it mean? It means like if you are here in the volume, inside the volume, and you leave the volume and you cross the surface, you might return back to the same volume. So this is a re-entrant surface. Re-entrant surface. So you cross the surface in more than 2 points. Okay, guys? So you cross here, you cross here, you cross here, you cross here for the surface. Okay? But for this one, this is non-re-entrant, so if you go inside the volume and leave, you will cross the surface no matter where. You will cross the surface in 2 points only. Yes, guys? So this is non-re-entrant surface. So we'll assume that we have this. Then we'll evaluate now over the volume df3, which is dfz, df3 by dz, dx, dy, dz. So this will be dx dy df3 by dz dz. So I evaluate the integration now in the z direction. Okay, guys? In the z direction, this surface is non-reentrant again. It will cross in 2 points only. So I evaluate the function df 3 over dz from g of x and y to h and x and y, from the lower surface to the upper surface. But any z here is given by what on the lower surface? Any z point here is given by g of x and y, and any z point here is given by what? H and x and y. So df 3 by dz, this will give you what? df, what's the integration of df 3? Guys, df, integration of dx, x. So df is f, evaluated where? At z equal to this and z equal to this. And because I am left with dx dy, what's dx dy? Area in the region R, so I am doing this. So this will give us what? Dx dy multiplied by f3 evaluated at x, y, and z is equal to what? The upper limit, which is x and h and x and y, yes, minus f3 of x, y, and what? G, x, and y, all evaluated at R. Does it make sense for you guys? Make sense for you? Then now, this is the right hand side of the equation. What's the left hand side? So let's call this, for example, 3, because this is 2a, 2b, 2c, and this is 3. So now, what's the right hand side? The right hand side is f dot n, yes, d a, but we were looking for what? For f3. We said that we will compare f3. Yes? So we are doing now f3 cosine gamma dA, which is just what? 2c. Okay, guys? So this will be equal to. Now, we are, here is the surface what? H, x and y. And the area dA is here. This is again k direction. This is the unit normal. And in between there is an angle what? Gamma. And this is what? This is h. And this is g of x and y. And this is h of x and y. Again. The other one is like this and like this. This is k, this is n, and sorry, k is up here. K is always in the positive direction. So the angle here is larger. So I can do f3 cosine gamma dA. What's the What's dA cosine gamma? dA is this area. The area is like this here, for example. Let's assume that our surface is like this. So the area is here. The area is here, like this. So the area is here, the unit normal like this, and the k is in this direction. So if you wanted to get dA cosine gamma, all what you are doing is just making the area to be perpendicular to what? To k. because this is the cosine of the area, yes? dA cosine gamma. What's the area perpendicular to what? Z direction. So what's the area perpendicular to Z direction? Yes? Because dA cosine gamma is just the projection of dA in xy plane, so it is dx dy. Yes, guys? But this is from the upper part. Yes? From the lower part, it is what? Negative dx dy, because the angle between n and z is greater than 90 degrees, so this will give you a negative sign. Yes, guys? So now, when I decompose this will give me what? Instead of integrating over S now, here I am integrating over what? Over R, and it will give me what? F3 evaluated at what? X, Y, and in this surface, Z is equal to what? Dx dy, and here is the minus sign when I evaluate it at the lower part here. So this will give me F3 x, y, and g of x and what? And y, and this is dx dy. The negative sign comes from the fact that you have what? You have n makes a larger angle with the z-axis here. So we will call this 4. If you look at 4 and 3, are they equal? 4 and what? 3. So what's 4? The right hand side. And what's 3? The left hand side. So we prove that 2C is correct. Yes? So with the same argument we can prove that what? 2B is correct and 2A is correct. So this is the proof for the what? For the Gauss theory. Okay, guys? This is the proof for the Gauss theory. If, for example, you have a re-entrant surface, you can still prove that Gauss theory is correct. And all what you will do is, let's assume for re-entrant surface, you have something like this. And this is volume 1. So all what you will do is you will get an auxiliary what? Auxiliary volume V2. Okay, guys? And you will apply. So 1, you get auxiliary volume V2. Then you apply Gauss theorem over V1 plus V2 and over V2, and you will obtain the same. Okay, guys? So now when we put this auxiliary volume and we attach it to the volume V2, we made V1 plus V2 as what? Non-reentrant volume. Just you close it. So if you have a volume like this and you have like a donut in the middle, just get clay, put it there, and press it until you fill this volume. So this is V2 and V1, and they will form a one volume, for example. Then you will apply the Gauss theorem over V1 plus V2 and V2. Okay, guys? So I will conclude with Stokes theorem, and this is the last theorem. And we studied at the very early beginning of this chapter just a special case of a Stokes theorem, which was Green theorem. So Stokes theorem transform from from a surface integral of the curl of the function f evaluated over an area A to a line integral over contour for the same function f dA. F dot, or sorry, not dA, f dot dr. F dot dr. So if you have a surface like this, and this is the surface, and then you have an area here dA, and this is the normal to this area, and you have a function f evaluated inside this volume, or evaluated now, you get the curl of this function over, integrate over the area dA over this surface S. It is equivalent to integrating over a contour C for this function f over delta r here. And the proof, you will find it in the book, but if f is just a function of x and y, and it's not a function of what? It's not a function of c, then when you evaluate curl of f, this will give you df 2 by dx minus df 1 by dy. Okay, guys? If you have this curl of f dotted with, this is curl of f, you dotted with the unit normal, this will give you, and multiplied by area dA, this will give you just df2 by dx and df1 by dy, or this would be dfy and dfx, and this is dx dy. So you can prove that f is just fx in the I direction plus fy in the jth direction. If you apply, substitute this one here and this one here, you will end up with the surface integral of dfy by dx minus dfx by dy, all evaluated at dy by dx equal to the surface integral of f fx dy plus fy dx. What's this? What's this theorem called? Green theorem. So the Green theorem is just an approximation of the Stokes theorem, in case you have what? A function in 2-dimensional like this, not in 3-dimensional space. So the application of this is, if you have a function f and you take the curl for this function over a surface, if this curl of the function is equal to 0, it means that this function field does not rotate. So if you have a surface like this, and then here is a vector field f parallel to each other, so this field does not what? Does not rotate. The curl of this vector is equal to 0. On the other side, if you have a surface like this and your function is now a function like this, if you take the curl of this function, so curl of this function f is equal to 0, curl of this function f does not equal to 0, so no rotation, and there is a rotation on the field itself. So by this I will conclude with this chapter, and next time we'll start the differential equation, and it will be the topic that we will carry over until the end of the semester. So it will be first order differential equation, higher order differential equation, series solution for differential equations, and so on. Have a wonderful time. Did you have any questions, guys? Have a good day.